Just a clarification, that were my topics for my whole PhD. Now I'll present one of the topics of my PhD, which is the topic that deals with uncertainty in meteorological forecasts for flood forecasting. And particularly, in this study, I will present you this presentation titled Uncertainty Quantification and Spatial Biases Assessment in Precipitation Forecast, a methodology for real-time flood forecasting applications. So I'm Enrico Gambini, a third-year PhD student. So my supervisor is Professor Marco Mancini, and my co-supervisors are Professor Giovanni Ravazzani and Dr. Alessandro Ceppi. So, motivation of the study. So, as we know, rain is the meteorological factor that plays the major role in producing floods. But, of course, to do accurate discharge forecasts, we need to know not just how much rain will fall under our basin, but also possibly exactly where it will rain. But we know that meteorological forecasts are always uncertain. So, particularly in small catchments, we know that sometimes slight misplacement of forecasted rainfall can mean the difference between predicting a flood event and predicting basically nothing at all. This is true especially for small river basins. So the idea of this study is to propose a methodology to treat this type of uncertainty and develop a procedure to create probabilistic forecasts that are able to quantify this location uncertainty in precipitation forecasts. So, just to get you into the context, meteorological forecasts can be probabilistic. The way that are called in the meteorological terms, they are called ensemble forecasts. Basically, the idea is to produce not a single forecast, but more forecasts. So, to produce a scenario of forecasts. This is to quantify the uncertainty of the forecast. So basically, generally what is done is, since meteorology since atmosphere is predicting the state of the atmosphere is an initial condition problem, we perturb the initial condition with some perturbation, some stochastic perturbation, and then we see the evolving in time of this perturbation. So that we have basically at the end sort of probability distribution of the outcomes. And so the spread of these outcomes is what quantify how much meteorological forecast is uncertain. Of course, the more spread, the more the meteorological forecast is uncertain. The less spread, the more the meteorological forecast is certain, in the sense that we have more confidence in providing the forecast. Just to see the forecast that was delivered yesterday for the weekend, as you see, basically the probability to have rainfall this weekend is quite high, in the sense that a lot of members of this forecast are predicting rainfall. So we have, I would say, a quite confident forecast for this weekend that it will rain, unfortunately. But this is just to introduce you the context of probabilistic forecast. So originally, what we did to quantify the uncertainty in the rainfall location to be used for flood forecasting. So there was a study. The idea was of Dr. Alessandro Ceppi, that it was like we have the precipitation forecast and we can shift it uniformly in space according to the 8 cardinal directions and see basically how much it is sensible the output of the discharge forecast to the shifting in this precipitation forecast. So we can create an ensemble, so a probabilistic forecast of discharge prediction. So in the x-axis we have time, and in the y-axis we have discharge, according to all these possible shift locations of the precipitation. So basically, the product that we had was something like, for all these rigid shift in the precipitation forecast, we have some exceeding of the civil protection thresholds for flooding in each of these 40 directional sheets. And the idea now is, instead of shifting, so basically the quantitative precipitation forecast, like in these studies, so in an equiprobable way, why don't we search by analyzing the past episodes for possible preferential directions in which the meteorological model tends to mislocate these precipitation events. So I introduce you the study area where we developed this methodology, which is the hydraulic node of Milan. As you know, it is a very highly urbanized, with a lot of population area. We are talking about a total area with the major river basins of about 1,000 kilometers squares. And as we know, there is still a lot of flooding problems. And so this is basically also why civil protection wants to develop and do research again about forecasting flood events in this kind of area, also because the exposure of the goods is so high because there is a lot of population. And again, just to get you into the context, for instance, for the Seveso River, the big problem is that we had an increase, a strong increase of urbanization. So we passed from the 17% of 1950s up to more than 50% in our days. And we also did a study to quantify how much the return period diminished for the flood peaks, and we saw that basically only the increase of urbanization was able to explain the increased frequency of floods, of course. So the idea now is to, as I said, the idea is to, sorry, locked. So the idea is to see whether the meteorological forecast misplace in some direction the precipitation forecast. Okay, so what we did, we compared the forecast of a single meteorological model, limited area meteorological model provided by the ISAC-CNR, which is the MOLOCH model, 1.25 kilometers grid resolution, against an observed rainfall field, which is reconstructed using radar and rain gauges together. So basically, the radar image is used basically as a spatial weight for the rain gauges observations. Just to give a very detailed spatial rainfall field. So we did this comparison on 64 hydraulically significant and independent convective rainfall events between the period 2013-2022, where we have basically data both of meteorological forecasts and of rainfall observations. So again, just to be less technical and more divulgative, I said that we used convective rainfall events. This because This because stratiform, so we need to do a distinction between stratiform and convective rainfall events. So stratiform rainfall events is what generally we associate with rain, so what happens generally in the autumn season. So very long-lasting rainfall, very widely extended through space. Generally, the characteristics of this type of rainfall events is that they are spatially uniform, but with lower rainfall intensity. And also, in terms of predictability of the meteorological model, they are more predictable with respect to the dual, which is the convective rainfall, that is mostly associated with local conditions or local atmospheric instability. They have very high spatial variability, higher rainfall intensities. They are most common during summer, for instance. A thunderstorm is a convective rainfall event, and they are also less predictable. But what is important is that they are very concentrated in space. So here it is the point. So those are events that are very concentrated in space, and so basically, if my meteorological forecast predicts the convective rainfall events, slightly misplacing it by a few kilometers for a small basin, this can be the difference between predicting a flood or predicting nothing at all. So this is why we selected only convective rainfalls. So just to show you an example of what does it mean, so those were two flood events. One was stratiform during autumn, 15 November of 2014, and on the right we have a convective event. So as you see, a stratiform event has a rainfall spatial distribution which is very more uniform than the one for a convective event. Okay. So then there are of course other factors that influences a flood, so for instance also the antecedent moisture conditions, but just to let you see visually of what type of events we are talking about. So in the previous study of the shift target approach, the meteorological forecasts were shifted inside the domain using a fixed distance that was derived basically arbitrarily. Here we wanted to do a step in advance, and to quantify which is basically the average mislocation distance of the meteorological model, using a procedure which is well known in literature, using this score that is the fraction scale score. Basically, it is a score that compares spatial fields, so in this case we are talking about rainfall, and it basically answered the questions, what are the spatial scales at which the forecast is able to resemble the observation. So basically, it is saying what are the spatial scales at which, if you see the forecast and if you see the observed rainfall field, they are quite similar. And as you see, we have basically to compare the fraction of pixels that are exceeding a certain rainfall threshold, and the metric is quite good at defining what is basically the scale at which a forecast can be considered useful, so better than random. And generally, the scale at the scale at which the meteorological forecast starts to be useful is related to the average displacement error of the meteorological forecast itself. So basically, we followed the procedure that is described in literature to select which is this precipitation threshold percentile to define this average displacement error. So we know that we want to forecast for an area of about 1,000 kilometers squared. So we can select the proper percentile. Then we can enter with the curve to find basically which is the average displacement error of the forecast. Here we follow the procedure described in the paper of Mittermeier et al. Of 2021. And we get the MOLOCH forecast, the MOLOCH meteorological model displaces on average on these convective events of about 20 kilometers. And this is already, I would say, a result of this study. So what we did, we basically take the study area and we enlarged the domain of comparison of this distance of about 20 kilometers. In the previous study, as I said, it was something arbitrarily, so it was enlarged of 50 kilometers arbitrarily. Here, we also tried to quantify the average displacement error of the meteorological forecast in order to compare the rainfall observations and the meteorological forecasts. So, later what we did is basically how we can quantify for each of the selected events of how much the meteorological forecast misplaced the event. So as you see, for instance, in this event of 8 July 2014, we are on the upper left corner, the rainfall forecast. On the upper right corner, we have the observations. So basically, as you can see, probably here, the meteorological forecast misplaced the convective rainfall towards the northeast. So how we can try to search for this distance? We used an algorithm of pattern matching, which is something that is generally used also, for instance, in image processing. So basically, we take that grid, we shift it around the space, we compute a loss function pixel by that is a function that quantifies how much the image on the left and the image on the right are similar. And basically, when this loss function is minimized, we can find basically which is the direction in which the meteorological forecast misplaced the event. Okay, so here on the lower left corner, you see the meteorological forecast shifted to find the best match between the observations. And we can do it for different duration of rainfall, rainfall duration accumulation, and for all the 64 events. So then we can obtain basically a point cloud of all these displacement vectors. And this point cloud is used to find a probability density function that are able to quantify the error of the meteorological model. And this can indeed be used as a generator of shifted rainfall forecast field in order to obtain our probabilistic forecast. So this is what we get. So those are basically all the displacement vector for all the 64 events and for all the selected rainfall durations. To find the corresponding to the probability density function, we use the Gaussian kernel. And so basically, we can find this probability density function that is telling us that it is convenient for this meteorological model to shift the rainfall forecast towards the southwest, meaning, reasoning at the contrary, that in most of the cases, this meteorological model mislocates the rainfall convective precipitation towards the northeast. Okay. This must be looked at the contrary. And this is, I would say, our generator. This will be our generator of new rainfall forecast fields that are shifted according to that probability density function. This rainfall forecast will be delivered as input to an hydrological model to produce the probabilistic flood forecast. So the fact is that we wanted to use it operationally. So we cannot, I would say, do too much runs of the forecast. So we know that we have a forecast computation time of at maximum 3 hours, and we know that using our current computational availability, we are able to produce in 3 hours 400 forecasts. So the approach is we sample from this distribution 400 points, and we check that these 400 points are representative of the original distribution. And what we get is a good result. So with 400 points, we sampled points, we are able to well reconstruct the original distribution. So basically, those are the points. So you imagine it arrives the forecast, the quantitative precipitation forecast, and you shift the forecast according to all these points. We used this procedure for this event, which was a convective event happened in September 2023, there was a small flood in Milan. It was a missed alert because most of the meteorological models weren't able to predict both, I would say, the intensity and in particular the extension of the rainfall fields. And we tried to apply this procedure for this event. I would say, I want to clarify a thing. So this is not, we tried only for this event for now, but we don't want to, I would say, do validation only using this event. So this is just to illustrate how the procedure is and can be implemented in real-time operations. So basically, we have the 400 shifted meteorological forecasts. We plug them as input to our hydrological model, which is the first hydrological model developed here at Polimi, and we get this. So here what we see that in general the meteorological event was underestimated with what was observed. In fact, the thick blue line is the observed discharge in the monitor cross-section that we selected. The green thick line is the discharge forecast that we would have had if we didn't shift the precipitation. And all the other solid black lines are the shifted forecasts, in the sense that are the 400 discharge forecast obtained from the shifting of the meteorological forecast. Here what we have is that at least some of those were exceeding the yellow threshold, and this is for the decision-making process of civil protection is, I would say, crucial, because using the single green forecast, we wouldn't have the evidence to at least give a yellow warning threshold. And due to the precautionary principle that is used in civil protection, this would have been probably a yellow alert, at least. So just to show you where this method is able to produce good results and where not. So, of course, in this case, so where we have a forecast in which there is I would say good amount of rainfall, can be useful in the sense that, for instance, in this case, if we move the quantitative precipitation forecast on the right, we would have at some point something similar to what was observed in terms both of spatial distribution of rainfall and also of intensity of rainfall. But in case the meteorological model does not forecast anything, we can shift the forecast everywhere, but we don't have any, I would say, discharge event forecasting, significant discharge event that is forecast. So this is a limit of the methodology in the sense that we always need the meteorological forecast, and in some way the meteorological forecast must be, I would say, at least decent. I would say at least a decent meteorological forecast. So just to conclude for this study, we saw that for the MOLOCH meteorological model that we considered in this study, there is, I would say, an average misplacement for convective precipitation of about 20 kilometers. So 20 kilometers is a lot or not? I would say for this kind of river basin, it is a lot, in the sense that we are dealing with narrow and elongated river basins. So in this case, a shift of 20 kilometers is a lot, can mean the difference between a flood and nothing at all, as I said before. So, in particular, we saw that the MOLOCH model tends to mislocate mainly towards the northeast direction. We didn't find, I would say, at least till now, a physical meaning for this kind of systematic bias. Probably will be a topic for future works. So since MOLOCH tends to mislocate mainly towards the northeast, it is convenient for us to shift the forecast of the MOLOCH towards the southwest. Okay. Then for the development of the methodology, we propose to use a kernel density estimation procedure to obtain the probability distribution function of the 2D probability distribution function of the error of the meteorological model, sample from it, sample as much points as you can according to your computational availability, and also to, the specific application of this sampling. Okay, so I finished my presentation. Those are 2 QR codes if you want to see the group of Professor Mancini and a description of the best hydrological model. And so thank you for your attention.
Thank you very much, Enrico. Is there any questions?